let's take a look at this problem on the board. So as I said, there are two possible products. Products that I'm thinking of are not related to stereoisomers. That's not to say we won't make stereoisomers. So if we include all stereoisomers, there are four possible things that we can make. Right? So two of the products will have enantiomers related to them. Right? So you learn mechanisms, I teach you mechanisms. So when you're challenged with a problem like this, you can think through it mechanistically rather than just trying to memorize something that should happen, right, and come up with that product. So let's try to work through the mechanism first and figure out what's going to happen. Right? So when you look at the starting material, we're going over substitution. So obviously this is going to be a type of substitution reaction. What's the first thing that's probably going to happen? Or what type of substitution would this be? Yeah. SN2. Why would that be?
I just thought maybe essentially the oxygen reactions of the oxygen to kick off bromine.
Like a direct substitution. So this is a tertiary center, right? And so we have to interact with the carbon-bromine antibonding orbital. Right. So how available do you think that would be, or how easy do you think that would be to add to the SN1? Yeah. So the more substituted the electrophile, right, that points us, that suggests that it's going to be an SN1. Right. So for an SN1 mechanism, what would the first step be? Yeah. So in this reaction, bromine is going to leave, and we're going to create a carbocation intermediate. Right, and there are a couple of things that can point us in that direction, right, to suggest that this is going to be an SN1 mechanism. First of all, as I said, this is a tertiary electrophile. Right. Second of all, we have a weak nucleophile in the alcohol, right? So if we have a weak nucleophile, that means even if these two things interact, right, because the nucleophile is weak, it might not necessarily have the power to displace that bromide right off the bat. Okay, so we have our tertiary carbocation. What's going to happen then with this carbocation? Great. So methanol, take its lone pair on oxygen, add to the carbocation center. Right. Create a positively charged intermediate, positive charge on oxygen, and then the last step to get us to a stable product. Great. Okay, so we can use methanol, another molecule of methanol, pull the proton off of oxygen, and that gets us to one of our two products. So if we look at the course of this mechanism, right, there's 3 steps, 2 different intermediates. Is there anything that can happen to one of these intermediates, or is there any way that we can represent one of the intermediates?
I said like when it's tertiary carbocation, the pi electrons will shift towards the
Here.
Yeah.
Yeah, good. Right. So if you look at the structure of this tertiary carbocation, right, you can see that that's going to be a stable carbocation because it's tertiary. Right. We also have a pair of pi electrons that's in common conjugation with that empty p orbital. Right. So hopefully you could look at this 3-carbon system here and identify that as an allyl cation. Right? And draw a resonance structure that reflects the relationship between those pi electrons and the empty orbital. Right, so all we are doing in this step, right, to show the resonance, is just shifting that pair of pi electrons over to show that those two pi electrons are being shared between among the three carbons. Right? Is that going to be equal sharing? Are those two pi electrons going to spend as much time between these two carbons as they will between those two carbons, do you think?
Well, you said the tertiary carbons can be more stable as a carbon cation, so one can spend more time on the second one, the first one.
Yeah, so we could assume that this is probably going to persist a little bit longer, right? Or if we were to take a picture of this molecule, right? I don't want to make it seem like these two pi electrons are either going to be here or they're going to be there, right? We have to think about those two pi electrons being shared among all three carbons, but it's not equal sharing, right? They'll spend more of their time kind of in this state or something that looks like, in this state, something that looks like this state because it's a more stable carbocation, right? And a little less time in this state. Okay, nonetheless, this structure does reflect some of the overall electronic structure of that carbocation. And as such, right, the methanol, just like it can add to this carbon, the methanol could also add to the secondary carbon as well. Right? And so we're just changing up the mechanism to reflect that one cation. Right? And then in the last step, again, we'll take a molecule of methanol, deprotonate the intermediate acid that we're forming. Right? And that's going to get us to the second ether product. So I guess in total we're only making 3 products, right? Because there's only one, this is not a chiral center, right? So there's no enantiomer of that product, just these 2. Questions about this? So that is going to take us just into a short discussion on other electrophiles that we didn't talk about. So far, when we looked at electrophiles, we've only really looked at the substitution patterns or the number of carbons around an electrophilic center, right? But there are other things that can stabilize a positive charge other than just substitution. So things like conjugation. So in this molecule, SN1 or SN2 reactions would be possible, right? Because if we lose that leading group, we will form a stabilized benzylic carbocation, right? Just through conjugation. Same thing with the allylic group that we just saw. In this case, SN1 or SN2 reactions would be possible. So we can't just look at substitution, but we have to look at the overall electronic structure of these electrophiles. And understand, particularly with nearby pi electrons, right? Nearby pi electrons can also stabilize that empty orbital in the case of an SN1, right? So this is, I mean, this is technically a primary primary electrophile, right? And we said that primary carbocations don't form, right? Primary electrophiles don't undergo SN1 chemistry, and that's typically true, right? Unless you have some other way of stabilizing that primary carbocation, in this case, just through resonance, right? So mechanistically, again, if you lose the leaving group, we'll form the allyl cation, which is stabilized just because of pi electrons being in conjugation with the empty orbital. Right, so for some of these electrophiles, it's really easy to pick out, is this going to be an SN1 or an SN2 mechanism? Right, for some of the electrophiles, though, for others, stuff like this, we have to look at other factors in the reaction, other conditions in the reaction that might point us to one pathway or another, right? And there are actually even some examples where a substitution can undergo, where a molecule can undergo substitution through both pathways, right? If the energies of those pathways are close enough, or similar enough, right, then SN1 and SN2 mechanisms can occur on the same electrophile. Any questions about this? All right, so the other day, at the end of class, we looked at nucleophiles. And we rank those nucleophiles according to good nucleophiles and what we consider not good or poor nucleophiles. I think towards the end, right, when we got down to the bottom of that list, we were looking at alcohols and water. And we said that usually SN1, I think we said this anyway, we said that usually SN1 reactions will occur using these two nucleophiles, these poor nucleophiles, right? Where SN2, right, will use kind of all of the others on that list, all the anionic nucleophiles, right, and the amino nucleophiles. And we try to, in a way, we try to plan it this way just because SN1 reactions are not often things that we want to happen whenever we're doing chemistry, and it's because the formation of a carbocation often leads to a lot of other byproducts, and so we try to avoid that. We'll learn when we get into elimination chemistry in chapter 14. We'll see how when carbocations form, a lot of the time that can cause a rearrangement of the carbon structure to form a more stable carbocation, right, or a more stable product. So we often try to avoid those reactions where we're making formal carbocations, right? But if we are planning them, alcohols and water are often going to be the nucleophiles that we're using. And as a result, we are using these both as the nucleophile. Right? We've also seen these compounds being used as solvents as well, right? And in those cases, they're also going to be used as a solvent. And solvolysis, in this case, we're using, we're defining as reactions where the solvent also acts as the nucleophile in the reaction. Right, so we saw an example of that above, right, a more simplified scheme for this. Right, we'll just take a tertiary alkyl iodide, use the iodide group, form the tertiary carbocation. Right, that water is going to add, or the water is going to add to the cationic center. Form, in this case, the tertiary alcohol. All right, so that kind of leads us to the question of overall, what role does the solvent play in these reactions, in these substitution reactions? And I would say really up to this point, right, all through OChem 1 and up to this point, we've been kind of treating the solvent as a passive bystander, right? Doesn't really participate in the reaction. Its really only purpose is to dissolve everything so everything's in the same phase and all the things that we need to react can react, right? But how it dissolves that is really important, right? Because we kind of ignore the fact that the solvent, right, is interacting with these molecules. That happens, how it has to dissolve these molecules, but it is interacting with these molecules. And in a way, it can stabilize those molecules, right? So we can group these solvents into a couple of different classes. Based upon their structure, right, or their functionality, right? And the first class is going to be polar protic solvents. And so these are polar solvents that have an acidic proton, right? So these are going to be things like water, alcohols, acetic acid, and then there's another one, well, I'm not going to actually put it up here. We'll just leave it at that. All right, and so if you look at these three solvents, right, hopefully everybody can rationalize these as polar solvents, right? All of them have a polar oxygen that's connected to less electronegative, electronegative oxygen that connected to less electronegative atoms, right? The electron density is, for all of these, is typically far to one side of the molecule, right? So creating a polar molecule. So they're protic because they all have a proton that they can get. Okay? And polar protic solvents are typically going to be used for SN1 reactions, right? And they'll usually participate not just as the solvent, but also as the nucleophile.
I have a question. Is it polar protic or polar protic?
Yeah, thank you. That was a trick. Yeah, right writing is it's one of those things that we learn so early on that we stop paying attention to it after a while, right? It just kind of becomes natural. And then we make mistakes like this, or I make mistakes like this. In contrast, we also have polar aprotic solvents. Right? And these are likewise going to be polar molecules, but they're not going to have acidic protons that can donate or participate in these reactions. Right? So the common polar aprotic solvents that you would see for substitution are solvents like acetone, dimethylformamide, DMSO is another one that's complicated but often used for SN2 reactions. And then put one more here, acetonitrile. Right, and polar aprotic solvents are typically going to be used to promote SN2 reactions. All right, obviously not through solvolysis. So this is not to say, and this is really important, right? Because I think it's easy to, when you're learning organic chemistry, you're learning about substitution, to kind of glom onto this trend here, right? Look at a reaction, see that the reaction is using an alcohol as a solvent, and say, oh, we're using an alcohol as a solvent, it's got to be SN1, right? Or see that a reaction is using acetone or acetonitrile as a solvent, and say, okay, we're using this as a solvent, it's got to be SN2. That's not the case, right? The solvent does not determine the pathway of the reaction. We have to look at the nature of the electrophile, we have to look at the nature of the nucleophile, right? And then, right, after those two things, then we can look at the solvent, and if there's still any ambiguity, right, the solvent will kind of push us in one direction or the other, or give us a clue in one direction or the other which pathway a reaction might go through. Right, there are definitely SN2 reactions that can use alcohols as solvents, right? Definitely SN1 reactions that can use DMF or DMSO as solvents. All right, so we have to look at the other, I would say, more important or more impactful factors first before we look at the solvent and say, oh, the solvent is telling us this. Right, but the solvent definitely does play a role, and when we set up these reactions, we try to make them, as much as we can, go through one pathway, right, or favor one pathway. So let's look at SN1 first, right, and just draw a really, again, simple SN1 reaction. And then we're going to look at the energy of this reaction and try to understand how the solvent might affect that energy. So again, we'll, like we usually do, assume that this is an exothermic reaction, right? Product favored reaction. Remember, for SN1 reactions, the unimolecular reactions, we're creating a high energy intermediate. And the first step, right, the loss of the leaving group is going to be the rate limiting step. When we were comparing SN1 reactions the other day, when we were just looking at the electrophile, right, we said that this intermediate plays an important role. So how does that intermediate affect the rate of the reaction? So if I drew another energy diagram over this to represent a different SN1 reaction, right, and I drew that intermediate, say down here, so lower energy intermediate, how would that affect the course of the reaction?
Lower intermediate, be faster reaction.
Good, right? So whenever the intermediate is lower, right, the pathway that leads to that intermediate is also going to be lower in energy, right? So this will be a faster SN1 reaction, right? So anything that we can do to stabilize that intermediate state is going to help that reaction out. It's going to help speed up the reaction. So the question here is, how does the solvent interact with the reaction intermediates? Right, so these are our two reaction intermediates. If we think about intermolecular interactions, right, how the solvent might interact with both of those, right, how might that be going on, or what might be happening here? Alexis,
If there's like a hydrogen, or not hydrogen, sorry, water, would that like kind of attach to the carbon?
Yep.
Try to make that more stable?
Good, right? So we know mechanistically, right, if our nucleophile is water, as Alexis said, right? And this could be water and alcohol, right, acetic acid, right? We know that the oxygen is going to move towards that carbocation center, right? We can also come up with kind of a before that actually happens, we know that water is a polar molecule, right? And there's going to be a significant partial negative charge on that oxygen. And so water can surround this carbocation to kind of act like a pillow or a cushion to help stabilize that carbocation, so after the leaving group leaves, right, it's comfortable, it's not too terribly unhappy. Right, so I think we could rationalize this whether we're using polar protic or polar aprotic solvents, right? Both are going to be polar, both are going to have a part of the molecule that has greater electron density, right? And so that part of the molecule is obviously going to help stabilize the electron deficient carbocation center, right? If we're putting, like, if you can imagine if this was acetone, right? We can draw the same dots from the oxygen of acetone going toward that carbocation center, okay? But this is certainly how a polar protic solvent would stabilize this intermediate. right? But we can't forget about our leaving group, because what we don't want to happen is for that leaving group to once it leaves, get scared because it's so unstable, right, and just bond back into the carbon that it just left, right? So we also need to think about how the solvent is interacting with this molecule here. Yeah.
The water be going to the other rest of the hydrogen atoms, or?
Awesome. So we kind of think of it in a way like hydrogen bonding, although iodide is not really involved in hydrogen bonding, but Anne is right. So we have these hydrogens from water that have a partial positive charge. That can surround that leaving group, because the leaving groups in these reactions are often going to be anionic. Right, lowering the energy of that anion and making it less likely that it's going to come back into the cationic center, right, and react with the carbocation. Right, so essentially what that solvent is doing is it's stabilizing the intermediate state of the SN1 reaction, right? And because it stabilizes that intermediate state, the previous transition state leading to that intermediate is also going to be lower, right, resulting in a faster reaction. Right, so this is what I mean by it's not the solvent that determines the reaction pathway, right? But it can definitely help out or promote a reaction pathway over another, right? So this would be the case in an SN1 reaction. Here, maybe we're using a aprotic solvent, right? Whereas here, we're using a protic solvent. It's going to make that SN1 pathway that much faster. Questions about this?
Is there a difference between iodine and say like chlorine as an anion for this stability?
In terms of what's happening here,
Yes.
no. Yeah, we're not going. I mean, there is definitely a difference in iodide versus chloride. I would probably say a polar protic solvent would help out chloride reaction more than it would help out the iodide reaction, just because iodide on its own is already a pretty stabilized anion, right? Leaves very easily, whereas chloride doesn't leave as easily, right? So to have that cushion for chloride will be more important. But the polar protic solvent will stabilize both. Yeah. Other questions? Joey, yeah.
So, I mean, if you had something like acetone instead of water there, I mean, it feels like that would also have a positive, partially negative and partially positive side. So, like, why is that different than what water is doing? Is it?
Yeah, great question. It's really the degree of polarization of that molecule, right? So the difference between an oxygen and a hydrogen is much greater than the difference between a carbon and an oxygen. And the ability for the hydrogen to kind of surround that iodide is, I guess, easier than a bunch of acetone molecules coordinating a carbon, because there's a lot more stuff around that carbon. So we have to worry about sterics, right? How the acetone molecules are interacting.
Makes sense.
Other questions? Okay. So let's take a look at how polar aprotic solvents will help out SN2 reactions. Right, so for SN2, we're going to just take an alkyl bromide, treat it with sodium cyanide. We'll do this, say, in DMF. Right, the cyanide's going to add to the carbon, take out the bromide in one step. And that's going to allow us to form the nitrile. Right, if we look at all of these polar aprotic solvents, right, hopefully everybody can rationalize the polarity of all of these solvents and see that they don't have acidic protons, right, or don't have strongly positive proton on them. Right, and so this is a case where we want we want these two molecules to react, right? And we have an anionic nucleophile. Okay, and the only case where, not only case, but really the most notable case where we're not going to have an anionic nucleophile is where we're using amines as nucleophiles. Right, but otherwise, typically when we're doing SN2 reactions, right, we're going to have an anionic nucleophile. And we want that anionic nucleophile to be as reactive as possible, right? So when we're doing these reactions, I'll use the green line as an example of doing a reaction in a polar protic solvent. Right? And the purple line is an example of doing a reaction in a polar aprotic solvent. Right? And we're really thinking about how that solvent is going to be interacting with the cyanide, right? With the nucleophile, the anionic nucleophile in this case. Right, so if we have Cn minus, right, we saw with the polar protic solvents, because of that really positive hydrogen, right, they can stabilize anions really well. Right, so if we're using methanol as the solvent in this case, that methanol is going to serve as a cushion to help stabilize that nucleophile. Why would that be bad for SN2? Why would that not be ideal, I guess is a better way of saying it, for SN2.
To make the cyanide more stable.
Yeah, it'll make the cyanide more stable, like less reactive, less want to go to the bromide. Right? Whereas if we use a polar protic solvent, right, that same stabilization is not going to take place. Right? So in this case, it's really going to be dependent upon which is the better nucleophile, right, and which is the better leaving group. So as long as we can make this nucleophile really reactive, right, not stabilized by the solvent, then when it's in the reaction, right, it's not going to be, because it's not stabilized by the solvent, it's going to react the way that we want it to. Okay. Questions about this? Oh, yeah, this class goes fast. Okay, we'll end there. On Monday, we're going to get into some elimination chemistry. We'll talk a little bit more about a few details in substitution, but otherwise we're going to get into chapter 13 and start comparing substitution and elimination. Actually, we can